everyone, thank you so much for clicking onto the video. Today we're going to be looking at group 7, so the halogens. And we're going to look in the trends in electronegativity and boiling point, and we should be able to explain the trend in electronegativity and the trend in the boiling point of the elements in terms of their structure and bonding. And then we're going to look at their trends in oxidizing ability of the halogens down the group, and then their reducing ability. We're also going to look at the use of acidified silver nitrate solution to identify and distinguish between halide ions. And we're going to look at the trend in solubility of the silver halides in ammonia. And so by the end, we should be able to explain why silver nitrate solution is used to identify halide ions, why the silver nitrate solution is acidified, and why the ammonia solution is added. So now we're going to talk about group 7 elements. And these are called the halogens, and they're all nonmetals and exist as diatomic molecules. So, for example, fluorine exists as F2, so it exists as 2 atoms of fluorine in one molecule. So there are particular things to know about each of these halogens. At room temperature, fluorine is a pale yellow gas. Chlorine is a green gas. Bromine is a red-brown liquid, and iodine is a black solid. So these are really important to remember, because you can be asked about it, or when you're forming equations, sometimes you need stuff in their standard states. So, for example, when you're doing questions about Hess's law, maybe, and so you need to remember that fluorine and chlorine are gases, bromine is a liquid normally, and iodine is a solid. And so the trends we have for group 7 are that the atomic radii increases down the group. And this is because the number of electron shells increases. So, for example, fluorine is in period 2, so its outer electron is in 2p5, compared to chlorine, which is in period 3, so its outermost electron is in 3p5. So it has that extra electron shell, and so the atomic radii increases. The second trend we have is that electronegativity decreases down the group. Electronegativity is the power of an atom to attract the electrons in the covalent bond, the pair of electrons in the covalent bond. And so because the atomic radii increases when we go down the group, that means there's more shielding, so the electrons in that covalent bond do not feel as big an attractive force from the positive nucleus compared to atoms which are further up the group. And then the third trend we have is for boiling points, and these increase going down the group because they're all non-metals, and because they get bigger, they have more electrons, and therefore they have more van der Waals forces, which makes them stronger. So they have stronger van der Waals forces between the molecules, and so more energy is needed to overcome them. And so the group 7 elements at the bottom have much higher boiling points compared to the ones at the top. Now we're going to have a look at chemical reactions of the halogens. So halogens usually react by gaining electrons to form 1- ions, and so are oxidizing agents. So, for example, we have chlorine, and they normally form Cl- ions, and so they gain an electron, and so they are because they are taking away an electron from the thing that's being oxidized to reduce itself. Now, the key thing is that the oxidizing ability decreases going down the group, and this is because of that the electron shells. So you have an increasing number of electron shells as you go down the group, and so that means that when they're trying to attract the electrons from the thing that it's oxidizing, it gets harder and harder going down the group because there's less of an attraction between the positive nucleus and the electron that it's wanting to take. And so this is why the oxidizing ability decreases going down the group. Now we're going to have a look at displacement reactions. So halogens react with metal halides in solution, and the halide in that compound will be displaced, which means replaced by a more reactive halogen. So, for example, chlorine is higher up than bromine in group 7. So that means that it's a more reactive halogen compared to the halide, which is the bromide ion. And so when you put chlorine into a solution with the bromide, what happens is that the bromide is displaced. so the solution which is formed is now sodium chloride. And so the bromine is then formed. And we can tell if this occurs or not because bromine is red-brown. So it will have gone from being a colourless solution to a red-brown solution. And at the bottom we have a table just to summarise what can be displaced and what can't be displaced. So the general rule is that if something is higher up in that group, then the oxidizing ability is bigger, and so that will be a more reactive halogen. So fluorine is more reactive than chlorine, and chlorine is more reactive than bromine. And so this is why fluorine can displace chloride ions, and it can displace bromide ions and iodide ions because it's the most reactive halogen. And then that's why chlorine can't displace fluoride ions because chlorine is one down in the group compared to fluorine, but it can displace bromide and iodide. And one thing to note is that we can't investigate fluorine in an aqueous solution as it reacts with water. So following on from the displacement reactions, we're going to look at the colours. And so we've already learned that the more reactive halogen displaces the halide. And so we can see that for chlorine and chloride, there's no reaction because it's the same, because chlorine can't displace its own, but the chlorine can displace the bromide in potassium bromide, so a yellow solution forms. And then the chlorine can also displace the iodide, so a brown solution forms. So this is the same for bromine. Bromine can't displace chloride, and so there's no reaction and the solution remains yellow. But it can displace iodide, and so that's why the brown solution forms here. And then for iodine, iodine can't displace any of them, and so there are no reactions for all three, and it remains as a brown solution because iodine is a brown solution. And then observations if we add an organic solvent are that for chlorine and potassium chloride, it's colourless, so there's no reaction. And then for chlorine and potassium bromide, it turns yellow because the chlorine has displaced the bromide. And then for chlorine and potassium iodide, the chlorine has displaced the iodide, and so it becomes purple. And then for bromine and potassium chloride, there's no reaction because the bromine can't displace the chloride. And then bromine and bromide, there's no reaction, but it's the same. And bromine and iodide, the bromine can displace the iodide, and so it becomes purple because the bromine has displaced the iodide. And then for iodine and all of them, there is no reaction because it is the least reactive halogen. And the colour of the organic solvent layer in the test tube shows which free halogen is present in solution. So when we add an organic solvent, we get the free halogen present in the solution, and that's the colours that we see. And so that's why bromine is yellow and iodine is purple. And so you can see that all the colours in the table are either yellow or purple. Colourless for the potassium chloride and chlorine because no displacement happens. And at the bottom we have some displacement reactions. So going through the first one, for example, we have chlorine and bromide. So chlorine can displace bromide because it's more reactive halogen, and so it becomes chloride and bromine. And this is the same kind of logic for chlorine and iodide and bromine and iodide. Now we're going to look at the reactions of the halide ions. And so halide ions are always 1- ions, and that's because the halogens are in group 7, so they want to gain an electron. And so they form 1- ions, and so this means they can act as reducing agents because they can give away this electron to reform halogens, and so it reduces the thing that's trying to be reduced. And the thing to know is that reducing ability increases down the group, and this is because of the electron shells again, because the electron shells increases going down the group. And so this means that outer electron gets easier and easier to donate because the force it feels from the positive nucleus is smaller when you go down the group. Now we're going to have a look at reactions of sodium halides with concentrated sulphuric acid. So the first one we have is sodium chloride. Now sodium chloride reacts with sulphuric acid to form sodium hydrogen sulfate and HCl gas. And the HCl gas is actually comes out as steamy fumes. So that's when you know that this reaction has happened. And all the oxidation numbers haven't changed. So it's not a redox reaction. And this is just an acid-base reaction. So the acid is sulphuric acid and sodium chloride is acting as the base. Sodium fluoride does the same thing, but it produces hydrogen fluoride, which is a really dangerous gas. Now we're going to look at sodium bromide, and this is two different reactions which are happening. So the first reaction that happens is the same acid-base reaction as for sodium chloride. And so we have sodium bromide reacts with sulphuric acid to form sodium hydrogen sulfate and the hydrogen bromide. And again, the hydrogen bromide comes out as steamy fumes. And this is the acid-base reaction. And then the second reaction that occurs is because the bromide is better at reducing compared to the chloride. And so oxidation of this bromide occurs and reduction of the sulphuric. And so this is a redox reaction. So we have two bromide ions reacting with two H+ ions and sulphuric acid. And this forms sulfur dioxide, water and bromine. And the really important thing to remember about these reactions is what is formed and how they have distinctive features. So we get steamy fumes, and sulfur dioxide is a colourless gas, and bromine is a brown-orange gas, because you'll be asked questions as to what's produced and also what would you expect to see. So how they've actually got this bottom equation is that firstly they have bromide ions which have been oxidized, so they form bromine molecules and 2 electrons, and also the sulphuric acid, they've reduced that to form sulfur dioxide. And if you can't remember how to form these redox equations, then quickly go back to the redox chapter to have a look and remind yourself. So they've got these two equations where they've converted this sulphuric acid to sulfur dioxide by reducing it, and the bromide ion they've oxidized, and they've basically just combined these two equations together to form this equation. So now we're going to look at sodium iodide, and this is also two reactions, but we've got some extra steps in the middle. So first of all, again, what happens is an acid-base reaction. So important thing to remember is that with all of these, the first thing that happens is an acid-base reaction, and so steamy fumes is always produced. So we have the sodium iodide reacting with sulphuric acid to form sodium hydrogen sulfate and the hydrogen iodide, which are the steamy fumes. And then because the iodide ion is so good at reducing, it reduces the sulphuric acid further. And so first what happens is that, so we're looking at the steps in between. So we have 2 iodide ions reducing sulphuric acid. And first of all, we obtain some iodine, sulfur dioxide and water. So again, we get sulfur dioxide, which is a colourless gas. And this is the same as what we got for the sodium bromide. And then what happens is that, again, it's so good at reducing the iodide is so good at reducing that it reduces the sulphuric acid some more. And so what's formed after is some more iodine gas, and then sulfur, the solid, and this is a yellow solid, and also some water. And then the last thing that occurs, so overall what occurs is that it reduces the sulphuric acid to hydrogen sulfide, and this gives off a very distinct rotten egg smell, water, and iodine. So the iodine provides some purple fumes. So from this reaction, what we get is we get some hydrogen iodide, so that's steamy fumes, and we get some sulfur dioxide, which is colourless gas, sulfur solid, which is yellow, some hydrogen sulfide, which gives off a rotten egg smell, and also iodine gas, which will be purple fumes. And so it's really important to remember all of these equations and all the distinctive things that they produce, because you'll definitely be asked about it. The reason we can tell why all of these extra things are produced is because of the reducing power of the iodide, is because if we look at the oxidation numbers of sulphuric acid, hydrogen sulfide, sulfur dioxide, and sulfur, then we'll be able to see the oxidation number decreases. And so first, what we have is that we have sulphuric acid, which is H2SO4, and so the sulfur has an oxidizing number of +6. And then if we have a look at what is produced, we have this sulfur dioxide here. So sulfur dioxide, the oxidation number of sulfur would be +4. So it's been decreased because the sulphuric acid has been reduced. And then what's formed next is the sulfur. And so this is now going to have an oxidation number of 0 because it's an element. And so again, the oxidation number has decreased, which means it's been reduced further. And then the last thing which is formed is this hydrogen sulfide. And so the oxidation number of the sulfur would be -2. So this is how we can tell that it is because of the reducing power of the iodide that we can form all of these different things. We can use aqueous silver ions to identify metal halide ions, which are aqueous. So these metal halides all react with silver ions in aqueous solution, except fluorides because they're soluble in water. And these all form a precipitate of the insoluble silver halide. And all these precipitates which are formed have distinctive colours, so we can tell which halide is present. And so the first thing we do is we add some dilute nitric acid, and this gets rid of any carbonate ions or hydroxide ions, which will form silver carbonate and silver hydroxide, which are both insoluble. So here we have the 4 equations. So the first equation is when we're removing the carbonates by adding the nitric acid. So you can see the carbonate ion reacts with the nitrate ion and the H+ ion to form carbon dioxide, water, and 2 nitrate ions. So the nitrate ions in this reaction are the spectator ions because they don't do anything. And then to remove the hydroxide ions react with H+ and nitrate to form water and nitrate ion. And again, the nitrate ion is a spectator ion. And again, the nitrate ion is a spectator ion because it doesn't actually do anything in the reaction. And so then we have the formation of silver carbonate, which we don't want because it's an insoluble substance. So we could mistakenly think that was a halide. And so we have 2 silver plus ions reacting with a carbonate ion to form insoluble silver carbonate. And then also we might form silver hydroxide if there's some hydroxide impurities in there. So this would form silver hydroxide, which is insoluble. So the second step that we do in this test is we add a few drops of silver nitrate solution, and this should form the halide precipitate. So in the table we can see that silver fluoride has no precipitate because it dissolves in water. Silver chloride will have a white precipitate, silver bromide will have a cream precipitate, and silver iodide will have a pale yellow precipitate. So you just need to kind of remember that starting from the top to the bottom, chloride will have a white precipitate, and then that colour will become less white, is how I kind of remember it. So it's white, and then it becomes cream, and then it becomes pale yellow. And then further tests that we can do is we can add dilute ammonia and then concentrated ammonia. So silver chloride actually dissolves in dilute ammonia. So if you've got silver chloride and silver bromide and you can't really tell between the two of them because one's a white precipitate and the other's cream precipitate and they could be very, very similar, you could add dilute ammonia, and if it dissolves then you know for sure that it's silver chloride, compared to how the silver bromide doesn't dissolve in dilute ammonia. Silver bromide only dissolves in concentrated ammonia. And the way you can tell if it's silver iodide, if the colours are very, very similar, is if you add concentrated ammonia, because it doesn't dissolve even in concentrated ammonia. So when you add the silver nitrate, it'll form a pale yellow precipitate. And then when you add dilute ammonia, it won't do anything. And then when you add concentrated ammonia, it also won't do anything. And that's when you know that you have silver iodide. So now we're going to look at some questions. So for the first question, when concentrated sulphuric acid is added to potassium iodide, solid sulfur and a black solid are formed. And A tells us to identify the black solid. So we know that when we add potassium iodide to concentrated sulphuric acid, we have quite a lot of things forming. We have a rotten egg smell and some yellow sulfur and misty fumes, and there's quite a lot of other ones as well. And the black solid which is formed that we need to remember is solid iodine. So the solid iodine is the black solid. So it's easier just to remember everything that is formed and all the different aspects of them. So like what they look like and what kind of distinctive features they have. And so it'll really help you with these kinds of questions. And then for B, deduce the half equation for the formation of sulfur from concentrated sulphuric acid. So this is just a question of writing half equations. So if we start off with sulphuric acid, and then we end up with sulfur, first we need to balance everything that isn't oxygen and hydrogen. So that's already done because we've balanced the sulfurs. And then we add in waters to balance the oxygens. So we need 4 waters. And then we add in H plus ions, balance the waters, or the hydrogens, sorry. So we have 8 on this side, and we already have 2 here, so it must be 6 H pluses. And then now we add in electrons to balance the charges. So we've got plus 6 on the left, so we need 6 electrons on the left to balance it all. And then for C, when iodide ions react with concentrated sulphuric acid in a different redox reaction, the oxidation state of sulfur changes from plus 6 to minus 2. The reduction product of this reaction is a poisonous gas that has an unpleasant smell. Identify this gas. So the gas they're talking about is that rotten egg smell. And so we just need to remember what that is. So the answer is hydrogen sulfide. Or you can just remember the chemical formula of it, which is H2S. So before I move on to question 2, feel free to click off the video and try it for yourself first. So it says a yellow precipitate is formed when silver nitrate solution acidified with dilute nitric acid is added to an aqueous solution containing iodide ions. Write the simplest ionic equation for the formation of the yellow precipitate. So what we're doing is we're forming silver iodide. And so we have silver ions in solution, and we also have iodide ions in solution. And so what this forms is silver iodide, which is a precipitate, so it's a solid. And then for B, state what is observed when concentrated ammonia solution is added to this precipitate. So now we need to remember our tests for these precipitates. So extra tests that we do is that we add in dilute ammonia and then concentrated ammonia. And we do this if the colours are quite similar, because silver chloride produces white precipitate, silver bromide is a cream precipitate, and silver iodide is a yellow precipitate. So sometimes these three colours might be actually very, very similar. And so this is why we add in the ammonia to further distinguish them. So the sodium chloride dissolves in dilute ammonia, and then silver bromide dissolves in concentrated ammonia. And the thing to remember about silver iodide is that it does not dissolve in dilute or concentrated ammonia solution. And so the answer is that nothing will change. So there is no visible change.